In this video, we're going to look at a brief introduction to projectiles. A projectile is an object moving under the influence of gravity only. When we're modelling these up, we model now our projectile as a particle, we ignore spin and we ignore air resistance. The only force we say is acting on the particle is the weight acting downwards. This is what we call a flight path or trajectory. So this might be a golf ball hit from the floor, it comes up, follows the curve and then back round to the floor. This is a parabola and it's symmetric about the midpoint. What we're going to do is look now at the vertical and the horizontal velocity of the particle at different stages of the flight. So what we're going to do is start off with an angle of release. This is one of the important features. I'm going to give this an angle of release and I'm going to say that that angle is going to be theta. Often we have theta or alpha. So this now is the angle of release. That's one of the key features that we need to pick up. We will also have a speed of release. I'm going to call that u meters per second. I'm now going to put on the horizontal and vertical velocities. If we look now, initially we have a large vertical velocity. The horizontal velocity will remain constant. If we then come up along the flight path, the vertical velocity will reduce. The horizontal velocity will remain the same. So I can put this on and that horizontal velocity will remain the same. This one is going to get slightly smaller in terms of the vertical velocity. The horizontal velocity stays the same. If we now put another one on and decrease this size, this vertical velocity is now tending to 0. So what we're going to have is that, and then it will actually be 0 at the top of the flight path. So where we have this trajectory, we can say now that we've got a symmetric point, and at this stage the vertical velocity is 0. When we come the other side, assuming we start and finish at the same height, we're going to have exactly the same here, it's just going to be in the opposite direction. So again, my horizontal velocity remains the same. This is going to be now of the same magnitude as this one, but it's now going to be acting downwards. So if we do that, we can put that one like so. So that now mirrors this one. Then if we put the next one on, that one will be just here. And we can put this one on, and that will be in this direction. Shortly, we're going to see, using the Suvat equations, exactly why we have this constant horizontal velocity. So let's just put the two more here, and we will have now just like so. That one will come down there. So that's that one just here. So let's just put that one on. And then finally, we have the last one here. Again, we've got the constant horizontal velocity, and we've got a large negative vertical velocity. So this is going to be of same magnitude as this one, it's just going to be in the opposite direction. So let's just make that a little smaller, we'll make that one a little smaller as well, and that's what we get. What we're now going to do is look at solving problems with projectiles. We do this using the Suvat equations, and we split them up now into vertical and horizontal Suvat equations. So let's now look at the vertical motion. I'm going to collect the information using Suvat. S, U, V, A and T. We've got now an initial velocity. If we consider the vertical component of this velocity, it will be u sine theta. So we can write that this is u sine theta. We know that the acceleration is going to be minus g. G is 9.8 meters per second squared. This projectile is simply acting now under the influence of gravity. If we now consider the horizontal Suvat, so collecting this information, we've got the following. We've got the horizontal velocity, which is going to be initially u cos theta. If we consider that there's no acceleration in the horizontal plane, we can say this is going to be 0. I'm now going to take the Suvat equations, and there are two that we're going to look at in particular. V is equal to u plus at, and the other one is S is equal to ut plus 1/2 AT squared. If I now apply this first in the vertical direction, we're going to have the following. We can say that V is going to be equal to U sine theta minus AT, which becomes GT. This we're going to use a fair bit. We can say the displacement, and this is the vertical displacement, S will be equal to UT, so that will be U sine theta multiplied by T minus now 1/2 GT squared. So all I'm doing is simply substituting this in to the Suvat equations we've seen in the past. So UT, which is this part, minus 1/2 GT squared. So this gives us now the vertical component of velocity, and this gives us the vertical height. What we're now going to do is look at the Suvat now and use these particular ones for the horizontal motion. So we can say V is equal to U plus AT, and we can see that there's no acceleration in the horizontal direction, so we can say that V is equal to U cos theta, and that is why it's constant. If we look, we've simply got now the same magnitude right the way through. If we look at S, well, S is equal to UT plus 1/2 AT squared, and we're simply going to have now no acceleration, so this is going to be U cos theta multiplied by T. This gives us now the horizontal distance, or what we call the range. The range in this particular one, I'll just sketch on here, is going to be from where we hit this golf ball to where it lands. So that's what we call the range. If I put that on, that distance right there is the range. And we can find that now horizontally, saying S, or if you like X, is equal to U cos theta T. Y, the Y coordinate, is U sine theta T minus 1/2 GT squared. So let's have a brief recap. When we're modelling projectiles, we model them as a particle. There's no spin, there's no air resistance, and the only force is the weight acting down. That means the projectile is an object moving under the influence of gravity only. Later on, we will see how we can use the symmetry of this parabola to solve problems. So for example, at this point, we will have now a 0 vertical velocity, and we can now double up this distance to find the range. So we'll look at a few problems involving those particular types of questions, and then in a later video, we're going to do some exam style questions. So this is the trajectory, this is the range, and we have now an angle of release and a speed of release. The other important thing also is the height of release, and we'll look at a question involving a different height shortly. Okay, a particle is projected with speed 35 meters per second at an angle of elevation of 60 degrees. Find the time the particle takes to reach its greatest height. So let's go ahead and sketch this. Often a little sketch really does help out. So what I'm going to do is draw a parabola. We're starting and finishing at the same level. We don't know that we're finishing at the same level, but we know now that we're only interested in something that looks like this. So what we've got then is an angle of elevation. So this is the angle of release. That angle of release is 60 degrees. So we can go ahead and put that on. So this is going to be 60 degrees. And we're going to have now a speed of release. And the speed of release is 35 meters per second. I know that this is symmetric about this point, like so, and we can go ahead and work with this. So we've got this particle, we're given the information here. I'm going to use Suvat. So if we want now the greatest height, this is the greatest height at the top of the parabola, and collecting the information, if it's the greatest height, the vertical component of velocity will be equal to 0. We saw that on this one right here. So here the vertical velocity is 0, and we can simply plug that in. We know that the acceleration is negative g, and the initial velocity is going to be 35 sine of 60 degrees. If you're unsure about the horizontal and vertical components, just consider now if we put this on, if I put now this as the right angle triangle, What we're looking for is this perpendicular height, and we can see using SOHCAHTOA or trig ratios that this is 35 sine of 60. Okay, so we can work with this. We have 3 unknowns and we need to find the fourth. The fourth unknown now, or we say we've got three of these, we need the fourth one, and that is going to be t. So if we've got t, let's put this in. All we need to do is use v is equal to u plus at. So we've got 0 will be equal to 35 sine of 60 degrees. If you know the sine of 60 degrees, it's root 3 over 2. If not, you can simply put it in a calculator. And then we're going to have minus gt. So we know that g is 9.8, so this is minus 9.8 t. Solving for t, we can say now that t is going to be 35 root 3 over 2 divided by 9.8. So however you want to put that into a calculator is entirely up to you. So I could write this now if I wanted as 35 root 3 divided by now 2 lots of 9.8, which is 19.6. So you decide how it works for you, and we get 25 root 3 over 14. So 25 root 3 over 14. Giving my answer now to 3 significant figures, we can say that that is going to be 3.09. So 3.90 seconds, and that's now to 3 significant figures. Okay, at this stage, let's move this on. What else could we do from here? Well, we can tell the time that it hits the floor. If we wanted to, we could work out this time. It's simply going to be double this value. So if we double this up, we can say that the time it takes to get to here is going to be 25, so 25 root 3 over 7. And that would give us the time. All I've done is said, well, if it takes 25 root 3 or 3.09 seconds to get to this midpoint, where it's its maximum height and its minimum velocity right here, then we simply double that up. We could also go ahead and find the range. So if I was interested in the range, that's that distance here. So 2 ways I could do it. I could find now using the time it takes to get to the midpoint, that distance, or I could simply double up and find the distance here. So if we look at now with the horizontal, so the horizontal SUVAT, we know that this is going to be 35 cos of 60 degrees, and we've got a 0 acceleration, and we have now a time of 25 root 3 over 7 seconds. If we go back, we can say that the range s is simply equal to u multiplied by t, as we don't have an acceleration. So s is going to be 35 cos of 60 degrees is 1/2, and we're going to multiply that by the exact value of 25 root 3 over 7, and that will give us the distance, the horizontal distance, or the range. So if we do that, what we're going to have then is the following. So in the calculator now, if I just do that, I can multiply this by 2. Alternatively, I could have just found this halfway. So what I'm going to have from this is 35 times by 1/2 times by that answer, and that will give me 108.25 meters, and that is going to be the range. So say 108 meters, and that's the 3 significant figures. So that's what we have. So nice straightforward question, and we can look to use the vertical and the horizontal SUVAT equations to solve problems. Okay, a ball is projected from a point 5 meters above horizontal ground with a speed 18 meters per second at an angle of elevation of 40 degrees. We're asked to find the height of the ball above the ground 2 seconds after projection. So the last example had us with now the projectile being, or the particle being moved from the floor to the floor, or starting at the same level. What we've got here is something different. We have that this height of release has changed. So the height of release has now become 5 meters, and we need to factor that in to our answer. So this is going to be 5 meters. So the height of release is different now. So what we're going to have is something that looks like this. So if we release it, it will come round. It will still be a parabola, but we're going to be missing this part right here, and we'll see now that it will come down further. So if I put this on, and again this isn't mandatory but it might help you, we've got a 40-degree angle. Doesn't have to be massively accurate, so let's put that there. And this now is 40 degrees, so we've got 40 degrees, and this is going to be 18 meters per second. So we want to find the height of the ball above the ground after 2 seconds. Remember, we're releasing this 5 meters above the ground as it is. So we're interested now in the vertical suvat, so collecting the information. Let's go ahead and do this. We know the time is going to be 2. We know the acceleration vertically is negative g, and the initial velocity will be 18 sine of 40 degrees. We are looking for this value to add to 5. So using S, and writing this in, S is equal to ut plus 1/2 at squared, or, if you like, S is equal to ut minus 1/2 gt squared. We can say S will be equal to 18 sine 40 times by 2, which is 36 sine 40, minus 1/2, and remember g is 9.8, minus 4.9 t squared, t is 2, and that's going to give me 4. So let's go ahead and work that out. So we've got now 36, so 36 sine of 40 degrees. We're going to subtract away from that now 4.9 times by 4, and that's going to give me 3.54. So 3.54, we want this now above the ground. So at this stage it's 3.54 meters above this platform. So I need to add 5 to my answer. So that's going to be 8.54 meters above the ground, correct to 3 significant figures. Okay, let's now work out what time it hits the floor. So if I do this, I'm going to consider this point right here. I'm going to again look at the vertical suvat equations. I want to know what time it hits the floor. If we look at the displacement S, that's going to be negative 5. We've got 18 sine of 40 degrees. We've got negative g, and we want to solve for t. So we can use S is equal to ut plus 1/2 at squared. And we can say that negative 5 will be equal to ut. So that's 18 sine of 40 degrees multiplied by t minus 1/2 at squared. So minus 4.9 t squared. We've got a quadratic in t, so rearranging 4.9 t squared minus 18 sine of 40 multiplied by t minus 5 is equal to 0. So from here we've got that A, using the quadratic equation, is 4.9. We've got B is going to be equal to negative 18 sine of 40, and C is going to be negative 5. So let's put this in the calculator. With the quadratic, we're going to have 2 different answers, and we need to check which is valid. So let's go ahead and do that. So what we're going to have is the following. Let's just put in here. So if I do negative, and check it in degrees mode, 18 sine of 40 degrees. So 18 sine of 40, that's going to give me this value here. Just going to store that in the calculator as A. So using the quadratic equation, we need negative A, because this is give me B, plus or minus the square root of B squared, so I can put in A squared, minus 4 lots of A times by C, so 4.9 times by negative 5, and that's all over 2 lots of A, which is going to be 2 times 4.9, which is 9.8. That gives me that T, let's write this down, T is equal to 2.73, and that's seconds, and that's correct to 3 SF. If I look at the other value from here, swapping this over for a negative, so if I put that in as a negative, that gives me negative 0.37, and so on and so forth. Essentially what this is saying is now, if I continue the parabola, that's what we'd have just here. Okay, that's what we'd have. This is when it's for negative, but quite clearly we started, that works mathematically, but it doesn't work in reality. So we discount the negative, we can say that t cannot be equal to negative 0.373 dot dot dot. So it's this one right here. So that's what we've got. Now if we look at this right here, we could then find the range. If I wanted to, I could find the range, and we could simply work out this distance from here. We've got a time, so at this stage I would consider now the horizontal motion. So that we are looking for S. S is the horizontal displacement. We have this time which I can store in the calculator if I like, 2.73 dot dot dot. We're going to have the horizontal component of velocity, 18 cos of 40 degrees. We've got zero acceleration, so we can say S will be equal to ut. S, which is the range or the distance in x, is going to simply be 18 cos 40 multiplied now by our 2.73. So multiplied by 2.73 dot 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 and so on and so forth. So I'm just going to store this in the calculator. Let's get our 2.73 back. And that's this value here. Shift store A. So I'm going to now multiply A by 18, and do check you're in degrees mode, 18 cos of 40 degrees. That will give us now the horizontal distance travelled, which is 37.7. So that's that distance right there, 37.7 dot 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 and so on and so forth. If this was a slightly tougher question, they might ask us for the speed that the, whatever it is, a ball hits the ground with and the angle it makes with the horizontal. So let's try that. Let's push this out here. We're always going to have this horizontal velocity, which is going to be now constant. So if I build up now a vector, so triangle of vectors, we've got this one just here. This is going to be 18 cos 40. And I can find this one right here. This is going to be the vertical. So for this one, we can use V is equal to U plus AT. So V is going to be equal to now U, which is 18 sine of 40, minus the acceleration, which is G, multiplied by the time, which is the 2.73 that we've got stored in the calculator. So this is going to be 18 sine of 40 degrees minus G multiplied by our 2.73 and so on and so forth. So using basic Pythagoras, this one squared plus this one squared, square rooted, will give us the resultant velocity. So let's go ahead and do that. So this is now my answer. So if I bring back A, that is A. So what I'm going to do is the square root. We're going to have 18 cos 40, so 18 cos of 40 degrees. We're going to square that. We're going to add to that now 18 sine of 40 degrees. Then we're going to subtract from that now minus G, which is 9.8, multiplied by A, and we're going to square this. So that gives me now the root of 422, or 20.54. So it now hits the floor 20.5 meters per second, correct to 3 significant figures. So that's the velocity. Often students think it hits the ground with a velocity of 0. It will come to rest, but as it hits the ground, it's that instantaneous speed as it's hitting the ground. We can find the angle that it makes with the horizontal. We can simply say that theta will be the inverse tan of 18 sine 40 minus G multiplied by the 2.73, and then we're going to divide that by 18 cos of 40. That's going to give us the angle. We know now that the tan of the angle is the opposite over the adjacent, so we can work out this angle and find the angle that it makes with the horizontal. So quite a tough part to the question there, but pushing it on nonetheless. So that's a brief introduction. I'm going to save some more challenging, well, these have been challenging, we've made them challenging. I'm going to save some more challenging exam questions for later on. Just to show a couple of other typical examples that you might come across, we might have now, for example, a projectile that's now just simply shot across with horizontal velocity only, and it'll come down here. We might have another scenario where we've got a ledge and we have a projectile that's launched up and lands on the ledge, so something like that. We might have a scenario where we have a parabola, like so, and we want to find the time that it's above, let's say 5 meters. So we might want to find that. We want to find the time between these two. So we're looking for T1 and T2 and subtracting them away. Or we might have something in context. So for example, a basketball player chucking a ball through a hoop. And this one often gets students a little worried. If you think with let's put the basketball player on, if we now have a height of release, let's go from here. So we'll now have, let's put this on, we'll have something that looks like so. So let's just scribble this up. So if they chuck a ball and it comes in here, we might want to know what time it takes to get from here to here, or the distance from here to here. This is often one that catches students out, because we're going to have 2 times when it's this distance above the floor, and we just have to consider that it's going to be the second one. So that's a typical type of question. So let's just recap the basics. What we've been looking at are projectiles. A projectile is an object moving under the influence of gravity only. We say the only force acting on the particle is the weight acting down. Spin and air resistance are ignored. We know that the horizontal component of velocity is going to be constant. That will be the same. And we can use the Suvat equations to solve by splitting these into vertical and horizontal Suvat equations. We can use the symmetry of the curve, it being a parabola, to work out certain things. So for example, now if it takes t1 seconds to get from this point here to this point right here, then the whole distance, or the whole time, is going to be 2t1. That's assuming we start and finish at the same place. If you want to think about this point right here, the vertical velocity is going to be equal to 0. We could at this say also that t, the time it takes to get here, is going to be u sine theta over g. And I'll let you work out exactly why that is, and we'll come to that in a later video. And this one right here, of course, is going to be 2u sine theta over g. We call now the flight path the trajectory, and it's a curve, and we call the horizontal distance the range. So, brief introduction to projectiles, modelled as particles, and a very basic model of that. So in the next video, we'll go through some exam style questions on these.